Okay, the initial rate of decrease of X was, so we have, is it that, it could be that mole per, is it the mole liter -1 that's messing you up? Or is it something else? Just so you guys know, if you see this, you probably will not see it, except for when I use these AP type questions. When it says mole liter -1, do you guys know what that means? It means moles over liters, because if you had 3 to the -1, right, that would be 1/3, yes? So if you have liter to the -1, that is 1/liter. So you would have moles times 1/liters, which is the same as moles over liters. So in other words, molar. Okay, and the same thing with the seconds. So you would have molar per second. Okay, not that it really matters here because you're just doing ratios. Okay, so if the initial rate of decrease of X was 2.8 times 10 to the -3, we have a coefficient of 1 here. We have a coefficient of 2 here, so it's going to be twice as much. So that will be 56 or 5.6 times 10 to the -3. Yeah, good stuff. Anything else? $12 on the written? Yeah. Okay, when a burning match is touched to the wick of a candle, the reaction between the candle wax and the oxygen begins. When the match is removed, the candle continues to burn. Explain why the match is required to initiate the reaction, but is not needed once the reaction has started. So we have a candle, it's sitting there, it does not spontaneously burst into flame, right? So what is the purpose of the burning match? That's going to be energy, right? Because the flame is energy. And there's our little match. Okay. Now, we hold that to our candle. So here's our candle. Oh my God, my flame's getting worse and worse. That's okay. Okay, there's our candle. And once we have done that, what kind of energy is the match providing? It's providing kinetic energy, which makes the particles move faster, which means that they will have sufficient energy to get over the activation peak. Okay? So the flame increases the kinetic energy of the particles. Therefore, the particles collide with more energy. Therefore, some of the collisions will have enough energy to get over the activation peak. Or you could say to achieve the activated complex, or whatever, something like that. All right, now, so that's why we needed the match. Now we take the match away, but this thing keeps burning. Tell your partner, why does it keep burning even though we have taken away this match, which is providing that extra energy? What kind of reaction is this? Exothermic. Oh, guess what? This was also exothermic. Yes? So the flame here was providing the energy. Now we have a flame on the candle itself. So it's like a self-perpetuating sort of a thing. Because it's exothermic, it releases kinetic energy. So we increase the kinetic energy of the particles. And therefore, some of the particles collide with more energy. Well, the particles collide with more energy, so some of the collisions will have enough energy to get over the activation peak. Yay. Yeah, so it's the same argument as before. It's just the source of that kinetic energy is changing from the lit match to the burning candle itself. Did that make sense? I had one person nodding. Yeah? Okay, I got 3 people nodding, 4, 5, okay. Yeah, and if it doesn't make sense to you and you're too shy to say, no, it does not make sense, please explain it another way, then that is your problem. I can only ask, you can only answer. So, anyone want further explanation on that? Okay. Any other questions? Alrighty. Would you like your quizzes back? Yes. Timmons. Actually, Yuri, could you just leave for like 5 minutes? Yeah. Charlene. Shaina. Nadia. Cassia. Christina. Christina W. Morva. Yui Fei. Caitlin Craig is not here. Jeff. Hayden. Tiffany. Tiffany is not here. Julie. Catherine. Rayan. Rayan? Which way do I say it? Now I've confused myself. How do you say your name? Rayan. Rayan. Yeah. Okay, got it. Yun. Ashlyn. Sion. Kira. Atrin. Kevin. Yonghyun. Christina A. Ella is not here. Caitlin Kim. In. Did I miss anybody? Would you like me to go over any of the questions? Because I can. So if you would like me to go through any of these, I can do so. Yes.
And here, what's the difference mentioning this?
Well, I don't know why you have it so many times. I just asked you to identify the reaction intermediates.
So
Right?
we had this once, and then we had this
And then we had it
another-
again.
Yeah.
It doesn't. You just need to say CL.
Okay.
Yeah, it's just a little weird to mention it twice.
This
Yeah.
one was interesting because I didn't know that I could.
Yeah.
I didn't
Well,
notice
because
that I couldn't identify it. Yeah. And here.
Yeah.
And I didn't also get this one. I don't know why.
Well, you only lost 0.25. It's
Still
because you didn't do a
something.
very good job of explaining one step of a reaction mechanism. You didn't say it was in a reaction mechanism.
Why would I say?
Why would you say that? Because reaction intermediates don't exist if it's not in a reaction mechanism.
Or like only said within the reaction.
Yeah, but what does that even mean?
It's in the reaction. It's
Yeah, but so is an activated complex. It's in a reaction.
no activated complex is not in the reaction.
Yes, it is.
It is.
Yes, it occurs in the arrow of the reaction.
Okay. That makes sense.
Hi.
Oh, this. Can you explain this one to me? Because
This one?
yeah.
Well, you're gonna go down to your seat and you're gonna put up your hand and you're gonna say, I would like to go over number. Okay, we're gonna go over 1D. See, this is how it works. Because I guarantee you are not the only person who would like to go over this one. So here is our overall. The first thing to do whenever you have multiple steps and you're missing a step is to write the overall reaction at the bottom. Okay? So we're going to write the overall reaction. Now, where is the overall reaction? The overall reaction given above, and then I follow the arrow and it says this one, and then I keep following it. So it is this one here. Okay, so that's the first thing we're going to do is we're going to rewrite that down here. So we have H2 plus Cl2 goes to HCl. So that's number one. Write the overall reaction at the bottom. Step 2 is to box everything that you need in the reactants and everything you need in the products. Everything needed in the overall. So what does that mean? What it means is I'm going to go find an H2, and I'm going to say, do I have an H2 in the steps already? Yes, I do. So I'm going to box that. That is taken care of. I am not going to touch that H2 anymore. Okay, I'm done with it. Once it's in a box, do not touch it. I'm also going to say, oh, I need a Cl2. Do I have a Cl2 in my reactants? Yes, I do. I can pick whichever one I want. I'm guessing that the one at the top is maybe a catalyst, but I don't know. It doesn't matter. It's all just going to be mathematical anyway, so it doesn't matter which one you pick, okay? And finally, I need 2 HCl, and oh, lo and behold, I have 2 HCl. Now let's just pretend for the moment that I only had 1 HCl up here. So just pretend that this one was missing, okay? This is just to give you an idea of another type of problem. If that one was missing, I would write an HCl over here to make sure I had 2 of them, okay? But that's not the case, so I'm going to get rid of that, okay? So anytime you need something and it's not already present in a step, you can add it to the step that is missing. All right, now we're going to go through and cancel everything that can cancel. So step 3, cancel stuff. Okay, I have 2 OCl, and I have an OCl and an OCl, so that is also 2 OCl, gone, gone. I have an O2, whoops, and an O2 on either side, so those will cancel. I could cancel this Cl either with this one or with this one. I'm going to do it with the bottom one because it's tidier. I don't have to worry about coefficients because I've got 1 Cl here and 1 Cl here. If you wanted to, though, you could cancel it with the one up above. It does not matter, okay? So those cancel out. And I also have an H and an H, and those cancel out. So the only things I'm left with now are Cl2, and I don't want another Cl2 down there, right? Because I've already got, like, this Cl2 is this one, so I've already got that. So this Cl2 that I'm highlighting needs to get canceled. Otherwise, I'll end up with 2 Cl2 in the reaction. So I need to put it over here so that it will cancel out. Yes. The 2 Cl. Okay, so is this with shared electrons and full octets the same as this, which has 7 electrons in its outer shell, and this, which has 7 electrons in its outer shell? They are different. Yeah? Yeah. So yeah, they won't cancel out. So then you would say, okay, what else do I need to cancel out? Now I need to cancel out the Cl, which would go over here. 2 Cl, or Cl plus Cl, either way. Okay, good question. Yeah. Anything else you would like to look at? We are all good. I was just writing a few things over here. This kinetic energy diagram. If we have a higher temp, the peak should be lower, the peak should be wider, the entire curve should be wider, and the peak should move to the left to a, or no, sorry, to the right to a higher kinetic energy. Yes? So it would look like that. Whoa, I did a good job on that one. I don't always manage it, right? Now, some people got confused between a potential energy diagram and a kinetic energy diagram. I had a few people label this as the activation energy. But what am I measuring as I go up the y-axis? Am I measuring energy? No. Okay, I'm not measuring energy. I am measuring number of molecules. So that peak there would be the most common number of molecules at any given speed. So in this value here, maybe this is 40 kilojoules per mole, okay? Now, what does a catalyst do? A catalyst lowers, activation energy. So if I'm going to lower from 40 kilojoules to a smaller value, which direction do I need to move that line? To the left. So this is going to move to the left. And, you know, I could say, oh, maybe now that's 30 kilojoules per mole. So that would be the EA catalyzed. And it would be lovely if you labeled things. I know it didn't say to label it, but if you didn't label it, it is good practice anytime you make a drawing to do the labeling. Yes? And you could be like, higher temp. Anyway, wasn't asked for, so I didn't really mind either way. But anything else? Make sure that this doesn't touch. You never want that to touch because it never goes to 0. It's asymptotic. Okay? Yeah. Okay. What else did people have problems with in general? If you have a reaction mechanism, then you need to have however many peaks for however many steps. So this was a 5-step reaction, so you need to have 5 peaks. Also, you will want to read carefully because it says oxygen lowers the activation energy by 100 kilojoules. So a lot of people just must have missed that. So do read carefully because that would put the top peak here. And it should be the slowest peak, which is the tallest. Okay, so that would be our second one, step 2. And whatever else it does in between doesn't really matter. You can put those other peaks wherever you want, as long as you have 5 of them, as long as that one goes there, and then we're there. Some people, when calculating the activation energy, went from here to here. Is that the activation energy? No, that is the energy of the activated complex. Activation energy says, I'm starting here. This is how much energy I start with. How far do I need to go up to get to the activated complex? I need to go up this much. Okay, so that's our activation energy. And just making sure products are here. And so that would be delta H. Yeah, and it would be negative. All right, shall we move on to equilibrium? All righty. So you will want your blue book if you do not have a blue book. Blue books are over there, and the answer key is over there. And we're going to start by watching a video. Let's see, is this on? Yeah, it's on. Okay. I think I need a blue book. Okay. Why are we not going? Click, click. There we go.
Faster than your.
Okay. Let's make this bigger. And here we go. All right. This is a really short video. It's only 5 minutes long. So do we want to just watch it the first time without having to desperately write things down, and then watch it again and write things down the second time? Okay. And I'll put on the captions the second time, but just watch it and get the general idea the first time.
In this lesson, you will learn about dynamic equilibrium, the conditions required for dynamic equilibrium to be reached, and examples of systems at equilibrium. Imagine you are digging a hole. You got it? Imagine, as you are digging that hole, your friend is refilling it. If you are digging the hole faster than your friend, the hole gets larger. If your friend is filling the hole faster than you, the hole gets smaller. But if the two of you are working at the same speed, there would be no change to the size of the hole. The same concept can be applied to a reversible reaction. If the rate of the forward reaction, reactants to products, is the same as the reverse reaction, products to reactants, the reaction is said to be at equilibrium. This is called a dynamic equilibrium because both processes are occurring simultaneously, even though there is no overall observable change. For a chemical system, such as a reaction or a phase change, to be at equilibrium, it must meet two important criteria. First, it must be a reversible process. Second, it must be taking place in a closed system. A closed system is one where there is no exchange of matter, only exchange of energy. An example of a reaction at equilibrium is the reaction of hydrogen and iodine in a closed container to produce hydrogen iodide. At the start of the reaction, there is a high concentration of hydrogen and iodine, and the concentrations decrease as hydrogen iodide is formed. The concentration of hydrogen iodide increases as the forward reaction proceeds. As hydrogen iodide is formed, the reverse reaction is then able to occur. Over time, the concentrations of hydrogen, iodine, and hydrogen iodide remain constant. So what is happening here? The reaction of hydrogen and iodine to produce hydrogen iodide is occurring at the same rate as the decomposition of hydrogen iodide to hydrogen and iodine. So there are no observable changes, although both the forward and reverse reactions are occurring. This reaction has not stopped, but rather has reached dynamic equilibrium. What would happen to this reaction if the lid on top of the glass jar was opened? Please pause the lesson to think about this and resume when you are done.
What do you think would happen? Yeah, nothing would be left. Because what are those things? They are gases. Bye! Now they can't even react with each other because they're far apart, right? So you're never going to reach that state where they can go back and forth because they're too far apart to react.
If the lid was removed, the system is no longer at equilibrium as the reactants and products, or matter, would be able to escape the system. Liquid bromine equilibrates to form gaseous bromine at room temperature. Remember that this is not a reaction, but rather a phase change. Phase changes can also reach equilibrium under the correct conditions. As liquid bromine evaporates, gaseous bromine condenses. Since these two processes are occurring simultaneously at the same rate, there is no observable macroscopic change, but the system is in fact in dynamic equilibrium. In summary, a chemical system is said to be at equilibrium when the rate of the forward reaction is the same as the rate of the reverse reaction. There are no observable changes, but both directions of the reaction are occurring, so it is a dynamic equilibrium.
Okay, so that is equilibrium in a nutshell. All right, so let's go back and make sure we filled in everything. Okay, and we'll pause it as we go through. In fact, actually, why don't we just try without the video and then we'll watch the video if we need to, yes? In parts where it's very useful. All right, so we're going to imagine we are digging a hole. You are digging that hole as fast, as you are digging that hole, your friend is refilling it. If you are digging the hole faster than your friend is refilling it, tell your partner what happens to the hole. So if the digging is faster than the filling, what happens to the hole? The hole gets bigger, larger. Either way you want to say it, whatever, it's good. Now, if your friend is filling the hole faster than you are digging it, the hole is going to get smaller. But if the two of you are working at the same rate, there would be no change to the size of the hole. So in this analogy, what does digging the hole represent? Does it represent the forward reaction or the reverse reaction? We're going to just say forward, okay? Pretty much you have to define one of these. If the digging the hole represents the forward reaction, what does filling the hole represent? The reverse reaction. The speed of digging represents the reaction rate. The hole getting larger represents the concentration of the products getting larger, and the hole getting smaller represents the concentration of the products getting smaller. I need to redo this thing because it's like all in the right order. Anyway, whatever, doesn't matter. All right. The same concept can be applied to
In this lesson, you will learn about can be applied to a reversible reaction.
Okay, so up till now, we haven't much focused on reversible reactions. We've looked at reactions that mainly go just forward. Reversible reactions, but actually there's lots of reactions that go back and forth and back and forth. Yeah? If the rate of the forward reaction is the same as the rate of the reverse reaction, the reaction is said to be at equilibrium. Okay, we're going to write that out the first few times, but eventually I'm going to start writing it like this, Eq'm, because that's a long word and it gets tiring, okay? This is called I think it's dynamic equilibrium. Let's just check.
If the rate of the forward reaction, reactants to products, is the same as the reverse reaction, products to reactants, the reaction is said to be at equilibrium. This is called a dynamic equilibrium because both processes are occurring simultaneously.
Okay, so let's say this is called a dynamic equilibrium. Because both processes are happening or occurring simultaneously. And it's less about the simultaneous part, although that does matter, because it wouldn't be at equilibrium if it weren't simultaneous, okay? If they weren't happening at the same time. But that dynamic part Have you learned about equilibrium in physics at all? Ha, yeah. What kind of equilibrium have you looked at in physics? Static, usually. No? Well, if the forces are balanced, you'll be in static equilibrium because it will be unchanging, okay? Dynamic means changing. Okay, dynamic means changing. So what's happening? What's actually changing in this reaction? Well, reactant molecules are changing into product molecules. Product molecules are changing into reactant molecules. Whoops, I should say reactant molecules first, because that makes more logical sense. Reactant molecules are changing into product molecules, and product molecules are changing. The reason I'm changing the color of the changing, because it is important, right? That's dynamic. Looks like it's bleeding. That's my pen doing that. Into reactant molecules. So it's like when we're filling that hole and emptying the hole, even though the size of the hole is not changing when we're at equilibrium, there's still dirt flying in and out of that hole, yes? So that's the reactant changing into product and the product changing into reactant. Okay, so that changing there, that's why it is called dynamic. Now, even though both the forward and reverse reactions are continuing to occur, can you see any observable change? Will you see, oh, look, product is being produced? No, because it's being used up at the same rate. So if you have a certain concentration of product, that concentration is going to stay the same because you're using it up at the same rate as you are making it. So let's say our product was purple, yes? You will have the same concentration of purple throughout. As soon as that system is at equilibrium, you will not get a change in the amount of purple color because every time you make a purple molecule, you will also use up a purple molecule. So the amount of purple particles will stay the same. And after your test on Monday, we're going to do a demonstration that does that. I would have loved to have done it today, but I forgot to set it up. So I'm like, oh, well, we'll do it Monday. We'll do a demo Monday. Okay. It's kind of fun. We get to make a toxic gas. Super fun. It's a demo, but we will be doing an equilibrium lab as well. Okay. Either next week or the week after, one of those two. I just got to figure out if I've got everything set up back there because it does require a little prep. Okay. Even though there is no overall observable change, so there's no overall observable change. And I'm going to give you a new vocab word here. Observable changes are called macroscopic changes. Do you guys know the meaning of the prefix macro? Macro means big. So these are things that are big enough for you to see with your naked eye, okay? Or even, quite frankly, with a microscope. I know it says macro, and that's micro, but when we're talking about chemistry and we're talking about small things, we're not talking about things you can see with a microscope, because those aren't actually very small in the grand scheme of things. We're talking about particle level, which is millions of times smaller than what you can see with a microscope, okay? And we'll talk more about macroscopic changes later. I just wanted to introduce the word to you now so that you've heard it once. And like I said, we will talk more about it later. That is a vocab word. Okay. Don't worry, it will come back again. All right. I don't know what the words are supposed to be, so let's go and watch the video again for a second.
Even though there is no overall observable change. For a chemical system, such as a reaction or a phase change, to be at equal.
A reaction or phase change. There we go. Okay. So for a chemical system, such as a reaction or a phase change, we need two important criteria. What type of process does it have to be? Reversible. So would burning a candle be able to reach an equilibrium? No, because once you burn the candle, you cannot go backwards. You cannot be like, oh, carbon dioxide, water. Like even if you trap it, like you cannot get the carbon dioxide and water to turn back into wax. Okay. It must be taking place in a closed system. A closed system is one where there is no exchange of what with the surroundings. We can be more generic than that. Matter, okay? So there's no particles getting in, no particles getting out. Okay, and here it says, if we were watching the video and doing this live, we would pause the video. Even though the video doesn't mention it, there are 3 other criteria necessary for a system to be at equilibrium, giving us 5 criteria in total. Okay, so we have number 1 here. We have number 2. And then number 3, and this one always seems to be kind of like silly to me, but it is true. You have to have both reactants and products present. Can you have a reverse reaction if there's no products there? Right? You can imagine if we had a reaction where we had A plus B gives AB. And if we had no AB, A plus B, and we had no AB, we wouldn't be able to go backwards. Yes, so you cannot be at equilibrium if you don't have product to break apart. The A and B has to be able to break apart into A plus B. So even though it sounds a little bit obvious, it's true. Now, the temperature also has to be held constant. Because what does temperature do to a reaction? Yeah, temperature affects the rate of the reaction. And you know what? It affects an endothermic reaction and an exothermic reaction by different amounts. So it will speed up one more than the other, okay? Temperature speeds up. Oh, an increase in temperature. No, actually, I'm not going to put that. Temperature affects endothermic reactions more than exothermic reactions. We'll talk about why later. Just believe me for now. It affects endothermic reactions more than exothermic reactions. Now, what do you know about a forward reaction and a reverse reaction? One is going to be, if one is exo, the other is endo. Yes? So they're always going to be affected differently. Whichever one is endothermic, if we lower the temperature, it will slow down more, the endothermic. If we raise the temperature, the endothermic will speed up more than the exothermic. And if both rates are equal, and they both speed up, but one speeds up more, are they equal? No. And if their rates are not equal, are we at equilibrium? No, because we'll be making product faster or we'll be making reactant faster. And same thing, if we lower the temperature, what happens to the two rates? Forward and reverse rate will both. What does temperature do to rate? If I lower temperature, what happens to rate? It decreases, but one of them will decrease more than the other. The endothermic will decrease more than the exothermic. And don't worry about why. Like I said, we'll talk about that later. But it just means that that's why we need to hold the temperature constant, because if we are changing the temperature, we're changing the relative rate. They are no longer going to be equal, okay? So the rates will become unequal. And if they are unequal, are we at equilibrium? No. Okay. And our last condition necessary for equilibrium is that it's pretty much just restating this, but just being a little more obvious. The forward rate must equal the reverse rate. Okay, so we have this example that they gave us in the video where we have H2 plus I2 gives 2HI. And do you see this little double-headed arrow here? That's called an equilibrium arrow. It looks kind of like a little harpoon going one way and a little harpoon going the other way. We put the forward direction on the top and the reverse direction on the bottom, and that means it is a reversible reaction. It doesn't necessarily mean that we are already at equilibrium, but it means that this system, if we leave it alone, it will come to an equilibrium, as long as it is in a closed system and the temperature is constant and all of those things that we just mentioned. So at the start of the reaction, we have a high concentration. So what we do is we put some H2 and some I2 into a container. Yes? So we have a high concentration of H2 and I2. Now, what's going to happen to those concentrations as these guys react and start to form product? It's going to decrease because I'm going to start making HI. Now, initially, do I make very much? No, I only have a very little bit to start with. So the concentrations of H2 and I2 will decrease. As HI is formed, and the concentration of HI will increase. So at the start, you have no HI, then you have a small amount, then you have a bigger amount, then you have a bigger amount. What happens to the rate of the forward reaction, or no, sorry, of the reverse reaction as the concentration of HI increases? Of the reverse reaction and because you have your reaction rate test tomorrow, you might as well explain to your partner what happens to the rate of the reverse reaction. And remember, the reverse reaction is 2HI becoming H2 plus I2. So what's going to happen to the reverse rate as the concentration of HI increases? Explain in terms of collision theory. Off you go. Chat. So, anyone want to tell me what happens in terms of collision theory? Because the particles are closer to each other because there's more in the same space, right? More particles in the same space means more frequency of collisions, which means that the rate will increase. Okay. Whoops, more particles in the same space, therefore more collisions, therefore faster rate. Okay, you could say higher frequency of collisions. That would be a bit nicer language, but I don't have a lot of room to write there, so I'm just going to write more collisions. Like that? Yeah. Now we're going to ask the other question, because not only are we making products, so product concentration is increasing, but we are using up reactants, so reactant concentration is decreasing. So what happens to the forward rate as the concentration of H2 and the concentration of I2 decrease. Explain in terms of collision theory. So what do we think? So now we're looking at the forward reaction. Now we're looking at the black arrow. We're going from H2 plus I2 gives us 2HI, and the H2 and I2 concentrations are decreasing. What could you say? There are less particles. Huh? No, you're correct. The rate would decrease because there's less particles, although in the same space, and therefore there are going to be a lower frequency of collisions, and therefore the rate will be slower. Okay? I don't know where to write that. Oh, here we go. I could do it down here. Fewer particles. That's more grammatically correct than less, just in case you were wondering. Fewer particles in the same space. Therefore, fewer collisions. Therefore, slower rate. So what we're going to do is we're just going to, this is at the start, and we have reactants only. What? That does not look like reactants. It looks like some weird word that has no meaning. Okay. Reactants. And that should not have a T, it should have an L. Only. So at the start we have reactants only. And our forward rate, we're going to represent the rate by the size of the arrow. So the forward rate is fast. Yes? FWD means forward, so the forward rate is fast. At the start, when we have reactants only, what is the reverse rate? It's not just slow, it is... What if I have no products? So what is my reverse rate at the very start? I have 0, okay? Like the reverse rate is not happening. Reverse rate equals 0. So that's at the start. Now, as time goes on, what was happening to the forward rate? The forward rate was decreasing, so the forward rate is now medium. Yes? And what was happening to the reverse rate? It's increasing, so we now have some reverse rate. Yes? And we can have smaller and bigger. Yeah? And then we'll end up eventually where the two are the same. And when we get to here, we have reached what? Equilibrium. And that's all to do with the fact that your concentration of reactants gets smaller and smaller, right? This is if you start with reactants only. Concentration of reactants gets smaller and smaller, so forward rate gets smaller and smaller. Concentration of products gets bigger and bigger, so the reverse rate gets bigger and bigger. And so you'll start with one rate being really big and the other rate being 0, and eventually they will kind of let go until they match each other. Yes? And then we will reach equilibrium, and as long as you have a closed system and don't change the temperature, you're good to go. Okay? And we're going to graph that, but not right this second. As hydrogen iodide is formed, the reverse reaction is able to occur. Now, once we have reached equilibrium, what is happening to the concentration of H2, I2, and HI? Let's see what it says. I'm trying to...
It must meet two important criteria.
Well, this is kind of nice.
First, it must be a reversible process. Second, it must be taking place in a closed system.
Tell your partner what the other 3 criteria are. Okay, we need a reversible system. We need a reversible reaction. We need a closed system. What else do we need? Constant temperature. You've answered one already. I want someone else now. Forward and reverse rates have to be equal. And it starts with both. Both reactants and products have to be present. Yay. Okay? You guys got it. Very good.
A closed system is one where there is no exchange of matter, only exchange of energy. An example of a reaction at equilibrium is the reaction of hydrogen and iodine in a closed container to produce hydrogen iodide. At the start of the reaction, there is a high concentration of hydrogen and iodine, and the concentrations decrease as hydrogen iodide is formed. The concentration of hydrogen iodide increases as the forward reaction proceeds. As hydrogen iodide is formed, the reverse reaction is then able to occur. Over time, the concentrations of hydrogen, iodine, and hydrogen iodide remain constant.
Remain constant.
So what is happening here? The reaction of hydrogen.
They remain constant. So what is happening here? The reaction of H2 and I2 to produce HI is occurring at the same time. That one's a little weird to figure out. As the decomposition of HI. Okay, so these two processes are happening simultaneously. So there are no what? Observable changes. So you won't see an increase once you hit equilibrium. Although both the forward and the reverse reactions are occurring. And this right here, that is what makes the equilibrium what? The fact that the forward and reverse reactions are occurring makes the equilibrium dynamic. Okay, the reaction has not stopped, but rather has reached dynamic equilibrium. What would happen to this reaction if the lid on the top of the glass was opened? If the lid was removed, the system is not or no longer at equilibrium, as both reactants and products or matter would be able to escape. Yes? Dynamic means changing. So dynamic and static are the two different, they're like opposites, okay? So the reason that this pen doesn't move when it's on the table is because the force of gravity is balanced by the normal force pushing up on the pen. That is a static equilibrium, and that's why you see no change in the pen. But in chemistry, because we still have those reactant molecules reacting to form products, we have changes at the particle level and changes at the particle level going the other way, and it's those changes that makes it dynamic. Does that make sense? Okay, so changes occur at the particle level. Even though we can't see any macroscopic or observable changes. And that word for observable, macroscopic. So we're comparing the macroscopic observable level with what's actually happening to the particles. We know we reach equilibrium because the macroscopic properties stay constant. We know it's a dynamic equilibrium because if we could zoom into the particles, we would see H's and I's getting together and H's and I's coming apart, right? We have like, what, 1 minute? Okay, why don't we just call it a day there? Guess what your homework is? Study for your test, okay? Yes. Yes. Do I not have your email? You don't want your school email?
No, my school name.
Oh yeah, no, I have. All I have to do is type action,
Oh, okay,
and it
okay.
pops up, and it's like,
Perfect.
"Do you want action Barangi?"
Oh,
And I'm like, "Oh yes, that's the one. That's the one I want."
because we're teachers, we have to actually copy paste it from a school
Oh yeah.
site, and I cannot
Yeah.
search Miss Spence or Karen.
Yeah.
Nothing. I cannot search.
Okay, Karen.Spence at burnabyschools.ca.
Yeah.
Yeah, That will do it.
Okay, yeah, that would.
So if you type that in, that will work.
Mhm.
Yeah.
So thank you.
Yeah. Hi.
Then use the mark on here.
Because you didn't mention that a reaction intermediate starts with a product in one step of a reaction mechanism gets used up in a later step. So you needed to talk about a reaction mechanism because intermediates are only present if you have a mechanism. If you don't have a mechanism, there's no intermediates. So if it's a single step reaction, intermediates.
Thank you.
Yep. Yeah. Yeah, you can. Yeah. Yeah. Because it's still moles per liter. So you can do pressure of a gas, you can do concentration of a gas. Either works.
Increase the concentration
Of a gas. Yeah. 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 Okay. It's okay. I can get a version of the test. You started it. Yeah, no, it's okay. Yeah. You're welcome.
Hey, stop. Get out of here, go. Well, okay, I questioned it, so I know this. No, how? I know this. Just slow down. Oh, okay. What is that? Oh, right. Into it. Wait, I don't like what's this mess. Guys, I'm these are the same. Yeah. Oh, that's the guy.
Yeah. Our test was so. I had 30 minutes to do the book.
Well, he is.
And then so she was like, those parts that she did are basically steps, and those steps reach out. So basically, she was asking us how much of the square is 6 feet. So basically, the infinite sum of the square, which is the infinite sum of 1/1. Right? Right? I forgot it. It's 8 over 1 minus 1. I forgot.
In my brain. Does anyone have any questions from the review? I will answer some today, if you have any. I do. I'll give those back. But we'll do any review questions first. Review. Kinetics 8. Review. Projector. Yes, you may. Okay. Hmm? 28. That's okay. Sometimes easy things are not necessarily obvious, right? Okay, so here we have a graph, and we need to, number 28, we have a graph, and we need to find the rate of the reaction. I would use, any two of these points to figure it out. So I would look at that and I would say this is point 0.03246. So that's 0.036. And this one here is 0.024. So my delta Y, which is my change in moles, excuse me, is equal to 0.036 minus 0.024, which is 0.012. And then I want that over the change in time. Oh. Oh, okay. Yeah. That would make sense. Yeah. Cool. Other questions from the review? Oh, did you want me to finish it?
Yes.
Yeah. So we always need delta quantity over the change in time. So my time would be my delta x, which would be delta time. And so since I chose these 2 points here, I would say, okay, I'm starting at 2 and I'm finishing at 8. Oh, I sort of did this the wrong way around, but because they're all positive values, I'm not going to worry about the fact that it should be a negative rate because it's decreasing over time. We're just going to pretend. We're going to pretend that doesn't matter. So I'm going to have 8 minus 2, which is 6. Okay, and that's 6 seconds, and this is 12 moles. And so now we're going to have the change in moles over the change in time. So that's going to be 0.012 moles over 6 seconds, which gives us 0.002 moles per second. Yeah? Okay, cool. Yes. 95, yes. Yeah? Okay, cool. Okay, so we have, if the initial decrease in X was 2.8, now, one of the things that people find confusing about this is what is this liter -1, second -1 business? Yes, so I just want to mention that while we're here. Yeah. So if you had 3 to the -1, that just means 1 over 3 to the 1, which is just 1 over 3. Yes? So if we have liter to the -1, that's going to equal 1 over liters. And if we have seconds to the -1, that's going to equal 1 over seconds. So what we have then is we have moles times 1 over liters times 1 over seconds. And if we group this bit together, yes, that becomes moles per liter. Yes, times 1 over second. And then if I really wanted to, I could write it like moles per liter per second, or I could write it as molar per second or molar per second. So that deals with that kind of unit business. However, you don't actually need to understand the units to do this question. What you need to realize is that they are all the same, so the unit is irrelevant, okay, in terms of being able to solve the problem. Because when you're looking at the rate of one thing compared to another thing, you're always going to be using the coefficients. Okay, so we've got a 2 and we have a 1. So whatever rate x is going at, y will go twice as fast, because every time we use up one x, we use up two y's. Does that make sense? Yeah? So if we are using up x at a rate of 2.8 times 10 to the minus 3, then we're going to be using up y at 2 times that amount, 2.8 times 10 to the minus 3. And so that's going to become 5.6 times 10 to the minus 3. Anything else? Would we like our quizzes back? Yeah, okay. So I'll give the quiz back. You guys take a little bit and look it over. And then I will go over some of the things that were problematic with it, or if you have specific questions, you can ask about them. Okay, so Ellie. Ethan. Sarah. Jessica. Parker. No, sorry. There's no Parker. Do you guys know who Sarah Jessica Parker is, though? No, probably not. Isaiah. You guys don't know Sarah Jessica Parker? Oh my God, you're killing me. Kylie. Pardon me? I think so too. Do you know who Sarah Jessica Parker is? Yeah, thank you. Ryan. Not, oh yeah, you're here. Laura. Michelle. Okay, Ryan. Michelle. Laura. Shauna. Cher. Jonathan. Dorsa. Hannah. Not here. Cocolyn. Grace.
Thank you.
Haya. You'll take it for her. Erin. Minnie. There you go.
Oh my God.
Jody. G1R. Jenya. G1On. I'm sure there's a subtle difference between your first names that I'm not saying properly, but Samira. Thank you. Yes. Oh, that's a reaction mechanism. I got lazy. Mechanism. I was marking these quite late at night and I was kind of like, okay, Mac, close enough. Yeah.
On just one step or step?
In one step, in any step.
So it's only in one step out of all.
Well, so this reaction intermediate is produced in step 1 and it's used up in a later step. Our CL is produced in one step and then used up in a later step. It's produced in step 2. So in any one step, it can be produced in any of the steps except for the last step, and then it'll be used up in a later step. Does that make sense? Yeah. Okay, cool. Yeah.
I was just like, I didn't know I wrote 4. Like my head was thinking 3 before.
And you wrote 4? Oh, I'm sorry. That sucks.
I didn't get one here.
Okay. So we have time to, okay. It also lives longer than the activated complex, so we have time to check its process. I don't know what this means either, right? So where's my pen here? I'm like, to check its process. I don't know what that means.
I mean,
For an activated complex,
like activated.
what is unstable? What is unstable? What is unstable? And it won't stay in that position. What position is it staying in? Like there's nothing.
Like high potential energy.
That's not a position. That's an amount of potential energy.
Yeah, because of that, it has
Uh-huh.
like a position, whatever, and like it's not gonna stay in that position because it
Because
has
the molecule is moving.
because it has a high potential energy,
So it will not stay at that
it's
potential
not
energy.
stable, right?
So it's not stable. But when you say stay in that position, what you're talking about is a position in space, not a position in energy. So this is a different position in space. This is a different position in space. A position is like where you are. I am here. It has nothing to do with my energy.
Okay, what am I supposed to say?
Okay, so you should say it's unstable because it has broken bonds and it would like to form new bonds. It's just, yeah.
How can I say like
You can just say it's unstable
okay.
compared to the reaction intermediate is more stable than the activated complex.
So if I didn't write this word, it would be
You would have been 2 out of 2. Yes,
okay.
but you said something that did not make sense. So then, yeah, there we go.
I got it.
Yeah, yeah, yeah. Yes. Tess. Okay, so we need to at some point have a little discussion about how much labs are going to be worth. Okay, I don't like marking labs, and I hear a lot of people don't like writing them. I would be okay just giving you quizzes and tests, in which case quizzes are 10% and tests are 90%. Okay? And then when we do labs, you know what? Maybe we'll make them worth like 5% and you just like show me the work, like just the bare bones of the work, but you don't have to do like a formal, like write everything and do an analysis and yada, yada, blah, blah. Okay? Something like that. We'll work it out. So your tests will be worth between 80 and 90%, just depending on what the labs end up being worth. Cumulative, yes. Oh, if you want to check your grades for this class, I've been putting everything in Q4 because it makes doing cumulative grading easier. If you find that too much of a pain in the butt, I can move them all to Q3. But that is also a little bit of a pain in the butt for me because now I have to move them. I thought I was being clever this year. I'm like, I'm going to be clever because always up till this point, I've had to take all my Q3 stuff and change it into Q4 halfway through the semester in order to do cumulative. And I'm like, why don't I just start with everything in Q4? But maybe that's not the best idea. Anyway, regardless, you can decide if you want me to change everything over or if you're just okay looking in Q4. Yes.
Yeah, I don't know what happened here, but like repeating.
Hang on. Okay. Reaction is, I did this really late at night, so it might be that I just read it wrong. Intermediates are products of step of reaction mechanism. An activated complex occurs during a step of mechanism or during a single step reaction.
Yeah.
That's what I should have said. Yes, there we go. Yeah, there you go. Yeah. Hi.
Really bad. Are you sure there's like no way at all to make up for it?
No, but you'll be fine. There will be enough other things. It won't, you could get a 0 on a quiz and it would be okay in the end. Okay? Yeah. Hi. Oh, did I add it wrong? That's totally possible. Yeah. Okay. So we got 2, 4.5. Oh. 5. So that should be a 7. Yes. Okay. Let me change that in here. Yeah.
With this, is this 0.5 off or did I get?
Oh, I didn't even mark that one. What is wrong with me? Holy mackerel. You got all the things done wrong on your quiz. So that's going to be a 3. So that's going to be a 7.5. There we go. Share, and I need to change it here because this is the most important place. There we go. I know, right? It makes my life so nice. So when I make mistakes when I'm writing here, I can be like, oh, I didn't mean that. Before that, I used to have to scribble them out and say, oops, sorry. Yeah, it's good. Hi. Ah, okay. So the activation energy needs to get lower. Yes, because catalysts make a lower activation. Where is energy equal to 0 on this graph? So as we go this way, what's happening to the kinetic energy? It's increasing. So you have made the activation energy increase. Yeah, so it would need to go this way to have a lower activation energy. Yeah? Yeah. Hi. Oh, because of the CL was missing. Yeah, yeah. No worries. No worries. It's always worth checking because Cher can tell you I missed 2 half marks on her quiz, so always worth checking. Would anyone like me to go over how to find step 5? Yes? Okay. I thought so, because my other block certainly did. So, first thing you want to do, this is number, I don't know, it's the front page. Front page, quiz. Yeah.
I know what I did wrong.
That's okay. Write the overall reaction below the steps. So that's the first thing you're going to do when solving for a step. So we're going to write our overall reaction. And I'm going to draw a line so I know it's the overall reaction. And how do I know what the overall reaction is? Well, I look up here and I say my overall reaction is given above this one. I follow the arrow and there it is there. So that is an H2 plus Cl2 gives HCl. So that's first thing, write the overall reaction. Second, you're going to, yes. Oh, yes, it is 2HCl. Thank you. That's important. Second, we're going to make sure we have everything we need for the overall reaction. Okay, check to see we have everything we need for the overall reaction, which means that I'm going to say I need an H2, and I'm going to put a box around it because that way I can say, do I have an H2? So I look up through my reactants and lo and behold, I do have an H2. So I'm going to put a box around it. Once I have put a box around something, I don't touch it anymore. I can't look at it. It's as though it is not there. Okay? I also need to have a Cl2. Do I have a Cl2 in the reactants? Yes, I do. There's one right here. Okay, so again, leave it alone now. Now, finally, we need to have 2 HCl, and we have an HCl and an HCl. So that's good. Now I'm going to make a small change just so you can see what it would look like. What if there was no HCl here? Okay, what if that was just not there? Okay, the one I've scribbled out. If that were the case, I would have only one HCl, and I would need to provide another HCl in my step. Don't write this down though, because you don't need it because we do have it. Okay, but that's what you would do. If you were missing something, you would write it in the missing step. Okay, so if you're missing anything, write it in the missing step. Otherwise, just put a box around it. Wow. Yes.
Please get another copy so I can write down the right answer.
Yes, of course.
Green, I don't know why. Thank you.
Yep. Okay, so we're not missing anything though, so we don't need to write anything. Third thing we're going to do is we're going to cancel anything that will cancel. Do your canceling. So we go over here and we say, sorry, I have 2 OCLs on the right-hand side. I also have an OCL and an OCL on the left-hand side, which is the same as 2 OCLs. So those will cancel out because they are on the right-hand side and the left-hand side. I have an O2 on the left-hand side, but I also have an O2 on the right-hand side. So those will also cancel out. I have lots of, I don't circle these yet. I've got lots of CLs over here, and I have a CL over here. I can cancel it with either one. It doesn't matter. Okay, it'll all work out the same regardless. I feel like it's maybe a little bit easier to just cancel out the one that cancels with the one, but it doesn't matter. You could cancel out the other one and just leave one of them there, okay? If you were to have done it the other way, what you would do is you would say, okay, I'm going to cancel one of these with one of those, and that leaves me with a CL there, okay? Because I can only cancel one, yeah? But I'm going to go back to doing it the other way because it was just a little bit tidier, I thought. Okay, so I got a CL and a CL and those cancel. Is there anything else that can cancel? I have an H and I have an H, and those will cancel. And nothing else will cancel because a Cl2 is bonded together. And each of those atoms has a full valence shell, whereas a Cl plus a Cl, those are separate atoms, and each of those has only 7 electrons in its valence shell. So they're very different from one another. So I need to then cancel out the Cl2 because there is no extra Cl2 down here, right? I only have this one here that is that one there, yeah? So I need another Cl2. And it needs to go. I should get rid of all the rest of that yellow stuff because it's just irritating me. There we go. There we go. In order for that to cancel out, it needs to go on the right-hand side. So we're going to put a Cl2 there. And the only other thing left is the 2Cl, and it's on the right-hand side. Because there's no Cl in the product, I need to cancel it out so it doesn't appear in the overall reaction. And so it's going to go here, 2Cl. So this will cancel with this, and this Cl2 will cancel with this Cl2. So my final reaction first, or my final step 5 is 2Cl goes to Cl2, or you could do Cl plus Cl goes to Cl2. Okay? Either way is fine. Okay, so that is how you, and then anything that doesn't cancel, this is step 4, anything that doesn't cancel, you need to put into your missing step to cancel it out. Anything unboxed and uncanceled should be added to the missing step on the opposite side. So that it does cancel. Oakley dokley? I have to remember to drop by the drugstore on the way home and pick up a card. I'm going to my niece's baby shower on the weekend. But I got to fly to Calgary. So if your tests aren't marked by Monday, that's why, because I'm visiting family. Okay. All right, now up here, there were a few things that maybe people didn't notice. I saw that a lot of people just missed the fact that it said that the catalyst lowers the activation energy by 100 kilojoules, which means that the peak of the catalyzed reaction needs to be lower by 100 kilojoules from 400 to 300. So that means our peak of the catalyzed has to be at the 300 mark. Other things that we're missing from people, this is a 5-step reaction. And if you're given the mechanism and you know how many steps, you need the same number of peaks as steps. 5 steps, 5 peaks. Okay? And you should also take note of who is the slow step. That is step number 2. And so that's going to be your highest peak for that. So you want step 2 to be the highest peak, and it's going to peak at 100 kilojoules below, and then the first peak is going to be shorter. And it really doesn't matter where you put the rest of them, as long as they're shorter than the other one. Okay? Aaron, you need to draw in your dotted lines. Yeah? So you should be drawing in and be like, oh, here's my reactants. I'm going to draw in a dotted line, just maybe all the way across. Here's my products. I'm going to draw a dotted line like all the way across, because I think that's going to help you. I think it's just like a visual thing. Do you know what I mean? So our change from the reactants to the products, we're starting at 100. We're finishing at 50. So that is negative 50 kilojoules per mole. Make sure you write your units. One thing that was a really common error that a lot of people did was they said that the activation energy was 400 kilojoules. But for activation energy, we don't start from the bottom of the graph. Where do we start? We start from the reactant. So we're going to start here and go up there. Okay? That's our activation energy. Okay? What else was there? On our other side, for the difference between a reaction intermediate and an activated complex, there were 2 ways to approach that problem. You could have defined activated complex and defined reaction intermediate and gotten 2 marks, 1 for each definition, which does work. Or you could have pointed out the differences between the 2. The reaction intermediate is more stable than the activated complex. The reaction intermediate only appears in reaction mechanisms, whereas activated complex appear in both reaction mechanisms and in single step reactions. What else? I had something in my head and now it's just gone. Oh. That might help me. There might be some others as well, but those are like the first four that come to my mind. Or you could just define them. And if you want to know what the definitions are, you have your vocab sheet, right? Kinetic energy diagram. I nailed it for my other block, so we'll see if I can draw a good curve again. So the things you want about at a higher temperature, you want the peak to move right, which is a higher kinetic energy. You want the right-hand peak to be further right, the right hand of the curve to be further right. Which again means higher kinetic energy. You want the peak to get lower. To keep the area under the curve the same. And am I missing anything? Peak gets lower, peak moves over, peak gets wider. The peak actually does get wider. I think there's an image in your book where the peak doesn't get wider. I need to fix that. I stole the image from somewhere. It doesn't make me happy, but you know. So if you drew it and your peak wasn't wider, it's not the end of the earth. Okay, so here we go. La la la. Not bad. Not bad. Had a little difficulty at the end there, but yeah. Okay, so these particles out here are my fastest particles. My fastest particles for the hot temperature are faster than the fastest particles at the low temperature. Yeah? Even though technically the fastest particles are like, you know, at the end of the universe, right? Because you can get infinitely fast, theoretically, to the speed of light, I guess. I don't know. Anyway, and our average has moved over, so our peak has moved over. So this is an increase in kinetic energy, average, because that's our average. We have an increase in kinetic energy of the fastest particles. See how everything just gets more spread out? That peak gets, it's not like, I think because of that one picture, people tried to make the curve kind of pointy. It shouldn't be pointy. I don't know. Anyway, doesn't matter. What else? That's about it. You should try and make it look like the area under the curve is approximately the same, right? I did have a few people where it was like, you know, we had like, and I'm like, that is not the same area, dude. I know it got wider and it got lower and the peak went to the right, but it is not the same area. So try to make it at least approximately the same, yes? Because the number of molecules is the area under the curve and the number of molecules does not change, okay? Total number of molecules. All right, that's it. Any other question? Oh, activation energy. Some people got their kinetic energy diagrams and their potential energy diagrams mixed up. And I had a few people label the activation energy, and then they were like, oh, now it's been catalyzed. What is the problem with having the activation energy going vertically? What's on the y-axis? Number of molecules. Energy is not on the y-axis, so you cannot measure energy on the y-axis, right? Energy is measured down here, so this would be 0 kilojoules. This might be 40 kilojoules. And what does a catalyst do to the activation energy? A catalyst lowers the activation energy. Well, what happened? Where'd you go? Why'd you close? No. Okay, it's all right. We'll come back. Here it is. It's back. It's back. Okay. A catalyst lowers the activation energy. So if we want it to get lower than 40, it's got to move that away, right? So maybe it's going to go to, I don't know, here. And then that's going to be maybe 30 kilojoules. And that there is our new activation energy, is the 30 kilojoules. Okay, so this is moving is good. Okay, are we ready to start on unit 2? Okay, if you do not yet have a blue book, you're going to come and get a blue book, and the answer key is here. Blue book, answer key. And if you have to pass by this thing, close your eyes because it's bright. Oh. Oh, I'll take that one. You'll be like, wow, this is really easy. And you're like, hey, hang on, why are we doing this? Yes. Yeah.